So thank you for coming to my talk today. My name is Nazim, and I am working as an intern with the OMR compiler team here at the Warden Lab. So the topic that I want to talk about today is Lljb, and this is the first time that I'm talking about this project outside of my immediate team. And the whole motivation behind Lljb is to be able to compile LLVM IR using OMR JitBuilder. And we're going to learn how that is done. So what I'm going to talk about today is what motivated this project. And then I'm going to give you an overview of the Lljb project. And we're going to go a little bit more in-depth into the LLVM IR, or intermediate representation. And then we're going to follow through an example of how we can transform some LLVM IR to OMR compiler IL using the JitBuilder API. And then I'm going to talk about the current status of the project and show you some benchmark results, and then talk about the limitations and future goals. So what motivated this project is that LLVM is something that is used widely by many languages. There is Rust, Lua, Swift, Julia, and probably one that almost all of us worked with, Clang. So LLVM Compiler Infrastructure Project is a collection of compiler and toolchain technologies, such as LLVM Debugger, Lljb. And then they also have an implementation of the C++ standard library, Lljb. And then they also have a linker LLD, and then they provide multiple tools for creating language front ends, such as, if you want to create any front end for any kind of programming language, they provide a bunch of tools to help you do that. And there's also tools available for creating new backend compilers for new architectures. And there are many more components of the LLVM project, and we can spend all day talking about that, but that's not the point of this presentation. And one of the most important components of LLVM ecosystem is the LLVM IR. And it's the core language used to be able to facilitate the compilation of different source languages to different target platforms. This is something that we're going to discuss in further details later. So here's an overview of how compiler front ends generate LLVM IR from the different source languages, and then pass it on to the LLVM backend compiler component, and that IR gets optimized by the LLVM optimizer, and then it gets generated into native code by one of the backend compilers. So you can start from C++, and then use Clang, and then have LLVM generate for x86 using their x86 code generator. Similarly, the OMR compiler also uses its own intermediate language, which we call OMR compiler IL, and we might also use OMR IL or just IL interchangeably to refer to our intermediate language. And it takes the compiler IL as input, and then it performs optimizations on the IL, and then generates native code for multiple platforms. So while LLVM is mainly used for static compilations, the OMR compiler is more suited towards dynamic compilation situations. And because of that, it could be the better option for languages that are currently using LLVM as their JIT compiler and for their dynamic compilations. But the problem is that the OMR IL is a lot more complex than LLVM IR. We have a lot more operations. There are a lot more opcodes that we have to deal with than just simply generating LLVM IR. So that's where JitBuilder comes in. It's a library that provides an easy interface into the OMR compiler technology. and it's already used by a number of projects, including Lljb. It simplifies the process of constructing OMR compiler IL using JitBuilder API. So the JitBuilder API provides a number of services to construct OMR IL, such as add, load, store, and so on. You can even create control flow paths using services such as goto and if then else and so on. Having a tool like JitBuilder makes it easier for languages to make use of the OMR compiler with a lot less effort than extending the OMR compiler themselves. So now, what if we had a way to compile LLVM IR using the OMR compiler? That will make it a lot easier for many languages to try out the OMR compiler. And the kind of tool that we need for that is something that can translate LLVM IR into OMR compiler IL. And so basically, if any language has any kind of tool that can generate LLVM IR from their source code, then they can compile using OMR compiler with minimal effort. So that's what Lljb does. So it's a library that enables you to compile LLVM IR modules using the OMR compiler, and it takes LLVM IR modules as input and uses the JitBuilder library to generate compiler IL, and then the OMR compiler performs optimizations and generates native code for different platforms. As you can see here, we replaced LLVM backend entirely. We just start with the LLVM IR. We use the LLVM IR reader library to convert the IR into something that we can consume. And then Lljb uses the JitBuilder API to construct OMR IL. So let's look a little bit more into LLVM IR. So it's a static single assignment based representation, and the two key points to remember about the SSA form is that values can only be defined once, and values must be defined before they're used. But it's not always strictly SSA for LLVM IR because they do allow they do not require you to adhere to SSA for memory operations. And there are three different modes of representing LLVM IR. So we have the in-memory LLVM module object, which is the top-level entity enclosing all of the IR instructions. And then we have a compressed binary file that ends with .bc extension. And then we also have a textual representation, .ll. And in this presentation, we are going to mostly see .ll because it's it's both human readable and it's also something that can be easily consumed. So I feel like we should look a little bit into SSA so that the IR that you see in the later slides are a little bit easier to understand. So in this example, we have A equals 1, and then A equals A plus 2, and B equals A. So the rule that we're breaking is that values can only be defined once, but here we are defining A twice. So how do we convert that to SSA form? Simply, we just version the different variables. So A sub 1 equals 1, A sub 2 equals the previous definition of A, which is A1, A sub 1, sorry, and plus 2, and then B sub 1 equals A sub 2. In this, over here, we can immediately tell that B is assigned to the A sub 2 version of A. So compiler optimizer doesn't have to do any kind of reaching definition analysis to understand what version of a variable they should be worrying about. So let's look at a little bit more advanced SSA, and I want to talk about, I want to introduce you to the idea of P functions in SSA. So in this example, we have some code that's not really in SSA. The block 1 is similar to the example we've seen earlier, except we now have a branch where we evaluate if B is greater than 3, and then we go either to block 2 or block 3. based on that, and then we merge onto block 4, and then assign D the value of C, whatever we get from the preceding basic block. So now, converting this to as a SAFE form, for block 1, I've already talked about how that's done. And then block 2 and 3, there are 2 different definitions of C, which is why we have to label them differently. So we have C sub 1 equals 1, and then C sub 2 equals 2. And then when we merge onto 4, D sub 1 can be either C sub 1 or C sub 2, and we don't know that. And how do we? And that's where we need a phi function to evaluate where exactly we got here from. So that's where we insert a phi function, and the result of the phi function is assigned to a different variable, C3, and then D1 just takes C3. So in this example, if we arrive from block 2, then pick C1, and if we arrive from block 3, then pick C2, and assign that to C3, and D1 equals C sub 3 plus 1. So now that we have some understanding of the SSA form, we can look at some actual LLVM IR. So this is a very simple C++ program. We're just trying to do some additions, and I'm just using this example because it's simple and hopefully easier to understand as well. So in order to generate the SSA form of that, the IR for that, we use Clang++ as the front end, and we instruct it to emit as LLVM IR, and we generate add.ll. So here is how a module looks like. You're going to see many things in this module. I'm going to talk about some of the things here. The comments begin with semicolon, and then we have the target information listed near the top. And then a function can have one or more basic blocks. In this case, there's only one basic block. We're going to see how a function with different multiple basic blocks look like. And then each basic block is going to contain one or more instructions. And as you can see here, we don't really have any of the variable names in this over here. They've all been transformed into unnamed temporaries. So X, Y, and Z that we had previously is now %1, %2, and %3 respectively. And basic blocks are also assigned one of these % values. And it's not like the numbering begins with %1. There's actually a %0 too. We don't see it here, but %0 refers to the entry basic block. So, and then there's also going to be different function attributes near the bottom. And then there will be some metadata strings and metadata nodes that start with the exclamation prefix. So LLVM provides API, and I spoke about this before, such as, LLVM IR reader helps with parsing the human readable form and forming the LLVM module object, which is the in-memory representation of what you see in the textual form here. And the modules contain LLVM function objects representing each function that is either defined or declared in a module. And then every function contains an LLVM basic block object, and each of them represent a basic block, and every basic block contains LLVM instruction objects representing the instructions. And LLVM also provides API to visit each of these instructions in every basic block and provide an API to handle specific instruction type in a different way. And that's what we use for constructing the OMR IL, and we're going to look at how we do that later. So here's an example of running Lljb and our test program. What Lljb takes as an argument is just the module that we generated from a compiler front end, and it outputs the result of the function that gets run. A module can have more than one function, and in that case, we expect to find a main function and use that as the entry point into the module. So in the upcoming slides, we're going to understand each of those instructions we saw in add.ll, and then we are going to learn about the different JitBuilder services that can be used to construct equivalent OMR IL. And we're going to also learn about how LLJB manages mappings between these SSA registers or SSA values and the IL values or the named locals. So the first instruction from the IR that we saw is allocate. So what allocate does is allocates memory on the stack frame, and the return value that is captured in %1 is the pointer to the allocated memory. And also it specifies the type for which you're allocating the memory, I32. So you can read and write from the allocated memory using stores and loads, respectively. Sorry, the other way. So the equivalent JitBuilder API, or the closest to it, would be create local array. And create local array takes the first argument as number of elements to allocate for, and also you can also specify the element type to allocate memory for, and what the IL value returned corresponds to the address of the array that is allocated, and this is what we initially were using for local variables, but the problem was that we are accessing a slot in an aggregate, and the generated code is slow because our optimizer cannot see through these local variable accesses, and which is why we switched to define local. And the define local service, you can specify a variable name and the data type to create a slot for a local variable. And the problem with that was that, as you saw in the IR, that local variables don't really get a name, so we have to generate on our own some sort of a string and then map the instruction for allocation to that variable name. Once we switched to using define locals, it actually doubled the performance in certain programs. So the next type of instruction we see is store, which is used for writing to memory. And in this instruction, the first argument is what you actually want to write, which is I32.1. So it's an in32 constant. And the second argument is the location to write to, which is %1. So write constant 1 into variable %1. It doesn't return anything, so we don't really need new SSA value to store anything, to capture anything. And there are two different things we see here. One is that we have to create a constant, and then we also need to perform a store. So there are two different JitBuilder services we have to use to handle this instruction. So the first service is const in32, and you use that to create a constant 32-bit constant node, and there are different services for creating constants of other data sizes as well. And the returned IL value represents the created node. And then we have the store service where you have to specify the variable name, which is probably something we generated earlier, and we specify the value, the IL value to store. So and for that we use the return of that, of calling the const in32 service. And below you can see the example of the IL that is generated. So the next type of instruction we see is load instruction, and that is used for reading from memory, and it specifies the type of data to load, and the %4 variable is used to represent the return of this load instruction. And we have a similar service in JitBuilder API, and we have to specify the variable to load, and the returned IL value represents the load of that. So the next type of instruction we see is add, and there is a flag that's not really relevant to our presentation. No sign wrap is used to specify that the result of this addition is supposed to be a Poisson value, and it affects the behavior of certain instructions later, but not relevant here. And it takes the operands to add, and the returned value represents the result of that addition, which in this case is %6. And then we also have something like that for JitBuilder. We use the add service where we have to specify the two different operands that we want to add, and the returned IL value represents the addition. And the final instruction we see is the ret instruction, which is used for returning control flow to the caller. And it can be either a void return, or you can return any other value depending on the function return type. In this case, it's a int32 return type. And in JitBuilder, we also have a return service to handle something like that. And it can either be a void return or return of an IL value. So now that we understand some of the instructions and have an idea of some equivalent JitBuilder services to handle these instructions, we can go through the steps that LLJB takes to construct something similar to this into OMR IL. And there are two tables that we are going to have to maintain. And one is the LLVM value to variable name for the allocate instructions. And for everything else, we have to have a mapping of the LLVM value to the IL value table. So let's look at the first one. So for %1, define local, and we generate a name for that variable, R1. And then we map %1 to the name R1. And then the same for the others. As you can see, our local variable name table is growing. And then the next thing we do is store. And in this instruction, we are storing const int32.1. So we create that const node, and then we get the name that we stored previously, and we just look up that table, and we get R1. And then we can store const int32.1 into that variable. And same for the other store instructions. And as for load, we similar to what I spoke about. We get the name of the variable that is being loaded, and then we have to make a mapping of the result of this load. So the result of this load in the IR is being captured by %4, and we have to map the result of this load service into this table, and have %4 mapped to load get name %1. And then similarly for this instruction too, and then we perform an addition, and here we have to access that table to get the values that we have previously stored in the table, and the operands are %4 and %5, and the get function returns the IL value that have been mapped to %4 and %5. And then we perform a store into %3, and we get name will return R3, and we store %6, which is the result of that addition, into variable R3. And then we perform a load into %7, and then return %7. And this is the IL that is generated after that. And the OMR compiler generates native code. Yeah, I know what you're thinking. You might be worrying about the death stores here, but this is a problem I discovered very recently, and we'll look into later. So far, we only dealt with a single basic block, but in most situations, you're not going to have that. For example, in the function below, function on the left side, you're going to see that it generates more than one basic block. So I'll just talk a little bit more about how this works. There are 4 basic blocks in this function, and %0 corresponds to the first basic block. The second basic block is %7, and then %8 is the third one, and then the final basic block is %9. And you're going to notice that there are 2 types of branch instructions. There are a conditional branch instruction that takes 3 arguments, which is the condition, and then path to take if true, and path to take if false. And then there is the unconditional branch, which only takes the destination basic block as the argument. And then for conditional branches, they're usually preceded by a compare instruction. And you're going to notice one thing, that we are referring to values that show up in the branch instructions. We're referring to %7, which hasn't been defined yet, and which is why, like, we have to keep. And in SSA, you cannot really use a value before it's defined. So which is why, like, you're going to notice that there's a label tag when we are talking about basic blocks to kind of identify these as basic blocks and not regular SSA values to worry about. So in order to construct control flow, we use JitBuilder's orphan builder service to create IL builders and assign them to every basic block in the IR. So multiple basic IL builders allow us to create the IL specific to each basic block independently, and then they can all be connected together based on the branch instructions. So when we have an unconditional branch instruction, we just have to get the destination basic block and then use that to find out the IL builder that's mapped to it, and then use the goto service to create an unconditional jump to that basic block. And for the condition ones, it's similar. We have to get the condition value, and then we get the 2 different possible paths, and then we use if then else to construct the conditional path. And now we get back into phi nodes and how they look in LLVM IR. So phi nodes in LLVM IR are used to select a value based on the incoming basic block. In this example, %13 is assigned the result of that phi function. And over here, if we arrive from basic block %6, then the value that we pick for %13 is %8. If we arrive from basic block %9, then we pick %11. So how do we deal with that? Well, this is when when the turn-in select service is used. So select service is something that is used to evaluate a condition and then select either one of the values based on the condition, and then return the value that has been selected. And this service was actually motivated by the Lljb project to implement the select instruction, and now it has even become useful in handling of phi nodes. So here's an example of how the IL generated by this service looks like. So in this example, to determine whether we arrive from basic block %6 or %9, we just need to evaluate %8. So if %8 was true, then we would have arrived So what we need to do is evaluate %8, and if % is true, we jump to %9. Okay. So we use a select service and then map %13 to the return value, and then the only condition argument we have to use is %8, and then get %8 is the true value argument if we arrive from there, and then get %11 is the false value argument if we arrived from, which will be the case if we arrive from block 9. So the current status of the Lljb project is, so it has mostly been developed over a period of 6 weeks, and in addition to supporting all of the IR we have seen so far, Lljb also supports having multiple functions in a module. So that includes calling different functions, passing parameters, and we also support aggregate types such as structs and multi-dimensional arrays, and then accessing data in those aggregate types. And then we support different types of comparisons and arithmetic operations, bitwise operations, type conversions, and a lot more. So now let's talk about some of the performance numbers that we observed. And the device used for taking these measurements is a 15-inch 2015 MacBook Pro. And the time measurements that I have in my charts are just the time elapsed during the execution of the programs, and it does not include the time taken to compile them. And then there are 3 different modes of execution we used. So we use the LLVM interpreter, or LLI, with JIT enabled. And so basically, LLI with JIT enabled actually compiles all the functions before they're actually run. So it's entirely ahead of time. So, and then we also have a native compilation at O3 optimization level. And then we have Lljb running the code at warm optimization level. And the starting point of all of this program was were all C++ programs. And we used Clang to generate the IR that was provided to Lljb and LLVM interpreter. And Clang just straight up compiled natively, starting from C++ code into the executable. So here is the result of running Mandelbrot set with the iteration limit set at 3 million, just so that I could get a significant enough number to get a noticeable time difference measurement. And as you can see, the LLVM interpreter with JIT at O3 is significantly slower. And we are just a little bit behind natively compiled code. And I think that looks pretty promising given the fact that we were able to achieve such results in such a short amount of time. And then the next benchmark we used was generating the MD5 hash of a string that was of 10,000 characters, and it was done 100,000 times so that I could get a significant enough workload to do any kind of measurement. And in this case, LLI does pretty poorly, and natively it's 2.4 seconds, and Lljb compiled code takes 5.71 seconds. In this case, we're actually a lot more behind than the previous example. But yeah, these are just the numbers that we get right now. And hopefully we can investigate later and get closer to the native compilation. So currently, the limitations are that we don't have support for intrinsic instructions. LLVM provides a number of intrinsic instructions to perform many operations such as memcopy and memmove and so on. And we don't have support for that yet, but it is a future goal. We're going to work on getting that support in soon. And another problem is we don't have support for variadic functions, and that is more of a JitBuilder limitation, where there is no way to specify variadic functions. And this is something that I hope to see happening soon, and we'll look into implementing in the future. And the other problem is paths by reference for local variables. We use define locals for defining locals, and if we want to pass by reference to another function, we need some sort of a load address service, but we don't have that in JitBuilder yet. But that's another future goal that we would like to implement later. And then currently, Lljb only handles running just a single module at a time. In the future, I will be working on being able to load multiple modules and call functions between them. And we don't have any metrics for measuring runtime footprint of compilation. And I hope to get some sort of metrics that compare how much improvement using the OMR compiler brings compared to using the LLVM JIT. And finally, I would like to have the Lljb contributed to the OMR project. I see this as a very useful tool that could be used in a number of situations, and perhaps it will be a sub-project of JitBuilder. And I will open an issue in the upcoming future, and where we can have a discussion about where it can live. To summarize, so far we spoke about what motivated the Lljb project, and then we spoke about SSA and LLVM IR. And then we went over how Lljb constructs OMR IL from LLVM IR, and then we spoke about the current status and looked at some performance numbers, and then we spoke about some limitations and future goals. And if you have any questions, I'm happy to take them. Yeah?
The section where you were mapping LLVM to OMR IL, how do you programmatically decide if to call get name or get? Sometimes you need an IL value on the
Yeah, so I think you're talking about that. Yeah. Hold on, let me see an example if we have both being used. Okay, so here we use a generic get IL value. Okay, so the question was, how do you know when to use get name or when to use get value, get itself? The thing is, we maintain a table where we know what the local variables are. So what values are corresponding to the local variables. So in that case, we have this function called is indirect load or store. So if it's an indirect load or store, that means we are not actually trying to access a local variable. In that way, we know whether to get the name or whether to get the IL value, and then we get the appropriate function for the situation. Okay. Is there any other questions? Okay. Anyway, thank you very much for your time, and my name is Nazim, and you can ask me if you have any further questions later on. And thank you very much.